Welcome to Podcast Learn and Fun. Let's start today's journey of learning by taking a look at how scientists visualize the state of quantum systems.
Yeah.
Especially qubits.
Right.
You know how we use a globe to represent the Earth? Well, physicists use a similar concept called the Bloch sphere to represent the states of those tiny two-level systems.
Right.
Qubits.
It's a great way to get a handle on what's happening in the quantum world.
Yeah.
Without getting bogged down in complex math.
Okay.
Instead of equations, we can use this visual tool.
Okay, that makes sense.
Yeah.
But before we go any further, can you remind us what makes qubits so special?
Sure.
Okay.
Imagine a regular bit in your computer. It can be either a 0 or a 1.
Yeah.
A qubit, however, can be in a superposition.
Okay.
Meaning it can be both 0 and 1 at the same time.
Whoa, so it's like it's in two places at once.
Yeah.
Is that even possible?
That's the strange and fascinating thing about quantum mechanics.
Yeah.
The rules are different at that scale. The Bloch sphere helps us visualize this by representing each possible state of a qubit as a point on the surface of a sphere.
Okay.
The North Pole is the state 0.
Okay.
The South Pole is 1.
Nice.
And all the points in between are those mind-bending superpositions.
So the further a point is from the poles,
Yeah.
the more superposition-y the qubit is.
Right.
Does that mean some points represent a qubit that is more both 0 and 1 at the same time than other points?
It's not exactly that a qubit is more both a 0 and 1 at the same time,
Okay.
but rather that the probabilities of measuring it as a 0 or a 1
Okay.
change as you move around the sphere.
Mm-hmm.
For example, a point on the equator
Yeah.
represents a qubit that has a 50-50 chance of being measured as a 0 or a 1.
I think I'm starting to get the picture here.
Good.
So how do we actually know where a particular qubit sits on this sphere?
Yeah.
Is there some sort of quantum GPS we can use?
You could think of it that way.
Okay.
We use two angles,
Mhm.
theta and phi, to pinpoint the exact location of a qubit on the Bloch sphere.
Okay.
Theta, like latitude,
Okay.
tells us how far the qubit is from the poles,
Got it.
while phi acts like longitude,
Okay.
giving us a direction on the sphere.
Okay, so it's like a coordinate system for qubits.
Exactly.
But I've heard that there are these things called mixed states, too.
Right.
Do those fit into this picture?
Absolutely. So far, we've been talking about pure states,
Mm-hmm.
which are represented by points on the surface of the sphere.
Okay.
But in reality, qubits don't exist in perfect isolation.
Right.
They interact with their surroundings,
Mm-hmm.
which introduces noise and uncertainty.
So it's like the real world messes things up a bit.
Exactly.
Okay.
And that's where mixed states come in.
Mm-hmm.
When a qubit interacts with its environment,
Yeah.
it can end up in a mixture of pure states.
Okay.
Instead of being at a single point on the surface of the Bloch sphere,
Yeah.
it's like the qubit is spread out,
Mhm.
occupying multiple locations at once.
So how do we represent that on the Bloch sphere?
Right.
Do we just draw a bunch of dots?
We represent a mixed state by moving our point inside the sphere.
Okay.
The closer the point is to the center,
Yeah.
the more mixed the state is,
Okay.
meaning we have less certainty about which pure state the qubit is actually in.
So a point right in the center of the sphere would be like total quantum chaos.
Pretty much.
Okay.
It would represent a state where we have absolutely no information about what the qubit is doing.
Right.
We call this the maximally mixed state.
This is all so fascinating.
Yeah, it is.
But how does this visualization actually help us do anything with qubits?
That's where the power of the Bloch sphere really shines.
Okay.
When we perform operations on a qubit,
Right.
like flipping it or rotating it,
Uh-huh.
we're essentially moving its position on the Bloch sphere.
Okay.
Understanding these rotations is key to building quantum algorithms.
So it's like choreographing a dance for the qubit on this sphere.
That's a great analogy. By carefully controlling these rotations, we can manipulate the qubit's state and perform complex calculations.
Wow.
Yeah,
Okay.
pretty neat, huh?
Yeah, that's really cool.
Yeah. And to really understand how we manipulate these qubits, you need to understand the tools we use.
Okay.
One of the most important tools we have
Yeah.
are the Pauli matrices.
Okay, I've heard of those.
Uh-huh.
They're those matrices with the Greek letter sigma, right?
Yeah.
But I've always been a bit intimidated by them.
Sure.
What do they actually represent in this context?
They're actually not as scary as they seem.
Okay.
Think of the Pauli matrices as the instructions for how to move a qubit on the Bloch sphere.
So they tell us how to perform those quantum operations we were just talking about.
Exactly. Each Pauli matrix corresponds to a specific type of rotation.
Yeah.
around one of the axes of the Bloch sphere.
Okay.
We have the X, Y, and Z Pauli matrices, and they allow us to flip or rotate the qubit state
Okay.
in different ways.
So if we want to move a qubit from the North Pole to the South Pole,
Right.
we'd use a specific Pauli matrix to do that.
Precisely. We can even combine these matrices to perform more complex rotations. It's like having a set of building blocks for manipulating qubits on the Bloch sphere.
This is starting to make sense.
Good.
But earlier you mentioned that these rotations aren't always perfect.
Right.
Real-world qubits are subject to noise,
Yeah.
which can cause errors.
Exactly.
How do we deal with that?
That's a great question.
Yeah.
And it's one of the biggest challenges in building practical quantum computers.
Right.
Noise can make a qubit end up in a slightly different state than we intended, throwing off our calculations.
So it's like our quantum GPS is a bit off.
Yes, that's a good analogy.
Right.
And to address this issue, we use another important concept,
Okay.
density matrices.
Okay, those were mentioned before.
Right.
Remind me again what those are all about.
A density matrix is basically a way to represent a qubit's state when we don't have perfect knowledge of it. Remember how we said mixed states arise when a qubit interacts with its environment?
Yes, it's like the qubit becomes a bit blurry,
Right.
occupying multiple states at once.
Exactly. The density matrix gives us a mathematical way to describe this uncertainty.
Okay.
It tells us the probabilities of the qubit being in each of the possible pure states that make up the mixed state.
So instead of a single point on the Bloch sphere,
Right.
we have a whole distribution of probabilities.
You got it. And we can visualize this by moving our point inside the Bloch sphere.
Okay.
The closer the point is to the center,
Yeah.
the more mixed the state is, meaning we have less certainty about which pure state the qubit is actually in.
So the center of the sphere represents maximum uncertainty,
Exactly.
while points on the surface represent pure states where we know exactly what's going on.
Exactly. And the beauty of density matrices is that they allow us to calculate the expected outcomes of measurements, even when we're dealing with this uncertainty.
So even though we can't pinpoint the qubit's exact location on the Bloch sphere,
Right.
we can still make predictions about its behavior.
Precisely. And this is crucial for designing robust quantum algorithms
Okay.
that can tolerate a certain amount of noise.
This is all starting to click now.
Good.
So the Bloch sphere and density matrices work together to give us a complete picture of a qubit state,
Yeah.
even when things get messy in the real world.
That's a great summary. They're essential tools for understanding and harnessing the power of quantum mechanics.
Okay, I think I've had enough time to process all that. It's amazing how these abstract concepts like the Bloch sphere and density matrices
Yeah.
can help us understand something as complex as quantum mechanics.
It really highlights the power of visualization
Right.
in mathematical tools.
Yeah.
And speaking of real-world applications, you were curious about how this all translates into practical uses.
Yes, absolutely.
Yeah.
It's all well and good to picture qubits dancing on a sphere. But how does that actually help us solve real-world problems?
The truth is, quantum computing is still in its early stages.
Yeah.
But the potential is enormous.
Okay.
Imagine being able to design new materials from scratch, simulate complex chemical reactions, or break the encryption codes that protect our online data.
Those are some pretty big claims.
They are.
Can you give me some specific examples?
Sure. Okay.
Take drug discovery, for example.
Yeah.
Pharmaceutical companies spend billions of dollars
Right.
trying to develop new drugs. And a lot of that time is spent
Yeah.
trying to understand how molecules interact with each other.
I see. So with a quantum computer, we could simulate those interactions at a much deeper level.
Exactly. Instead of relying on trial and error or approximations,
Okay.
we could simulate the quantum behavior of molecules, allowing us to design drugs with much greater precision.
That would revolutionize medicine. What about material science?
Yeah.
I've heard that quantum computers could help us create entirely new materials. Right.
With properties we've never seen before.
You're absolutely right.
Yeah.
Think about superconductors, for example.
Yeah.
These materials can conduct electricity with zero resistance, but they typically only work at extremely low temperatures.
Right.
A quantum computer could help us design superconductors that work at room temperature,
Okay.
which would transform everything
Yeah.
from energy transmission to transportation.
Wow, that would be incredible. It seems like the possibilities are endless.
They really are.
But what about the potential downsides?
Yeah.
I've heard concerns about quantum computers breaking our current encryption methods.
That's a valid concern.
Okay.
Many of our current encryption algorithms rely on the fact that it's very difficult for classical computers to factor large numbers.
Yeah.
Quantum computers, however, are much better at this task.
Right.
If a powerful enough quantum computer were built,
Yeah.
it could potentially crack the encryption codes that protect our online banking, communications, and other sensitive data.
So it's a double-edged sword. Quantum computers offer amazing potential,
Yeah.
but they also pose new risks.
That's a great way to put it. And it highlights the importance of continued research and development
Okay.
in areas like quantum cryptography,
Yeah.
which aims to develop new encryption methods that are resistant to attacks from quantum computers.
I see. So it's like a race against time.
Yes.
We need to develop these new security measures
Right.
before quantum computers become powerful enough to break our existing codes.
Exactly. And it's a race we can't afford to lose.
Well, this has been a fascinating journey into the world of quantum mechanics. I feel like I've learned so much about the Bloch sphere,
Good, I'm glad.
density matrices,
Yeah.
and the incredible potential and challenges of quantum computing.
It's a truly fascinating field, and we've only just scratched the surface today.
Right.
Who knows what amazing discoveries await us in the future?
That's what makes it so exciting. There's still so much to explore and understand. Thanks for guiding me through this quantum landscape.
It's been my pleasure, and I encourage all of you listening to keep learning and exploring the wonders of quantum mechanics. You never know what you might discover.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.